Right.
Okay,
Perfect.
has that come up?
Yes, perfect. I can see your screen. Go ahead.
Okay, so this is my talk on our paper, Are Contrastive Explanations Useful?, which is done by myself, Yaji Sripada, Wei Pang and George Coghill. We are from the University of Aberdeen and Heriot-Watt University, and my work is supported by the EPSRC. So when we're looking at making explanations useful, we need to go back to some of the social and cognitive science about what makes explanations useful. And our work follows the work of Tim Miller, who has said that explanations need three things to be useful. They need to be contrastive. So we need to say not why an event happened, but why an event happened instead of another event. This work uses the lending domain. So we'll be mostly asking not why somebody has been rejected the credit, but what they could change to make them accepted. We need to be selective, which means we don't want to give everybody all the causes of an event when we can just give them a relevant subset. And so in this work, we don't want to give everybody their whole record as an explanation when we could just say, earn more money and your loan will be accepted. And also, explanations need to be social because they're a transfer of knowledge from the explainer to the recipient. So we need to pay attention to how we say things as well. So contrastive explanations, which are what we want to look at, these are a collection of counterfactuals that say what needs to change in order for somebody to move from what happened to what they want to happen. And these are the best fulfillment of our desiderata from the previous slide because they're naturally contrastive because they're counterfactuals, and they're selective because they only give the changes to the information, not all of the information. So when we make counterfactuals in experiment, we use two methods. The first is DICE, which is a published method by Mofalal et al., which has been around for a little bit and is used in the field. This needs access to the decision model, and it optimizes on the proximity to the decision boundary and the diversity of the counterfactuals generated to each other. The other one we use is an artificial immune system algorithm called OptAINet, which is our own work on an existing algorithm that we are applying to explanations. This again needs access to the decision model, and this optimizes on proximity to the boundary. So because this is our own work, just to make a quick explanation of how it works. So what happens with the artificial immune system is we start off by generating a set of counterfactuals randomly. These must be of another class to the decision we want to explain. And then we mutate these counterfactuals so they move closer to the fact, our decision. And the further in distance the cells are away from our fact, the more they mutate, the nearer they are, the less they mutate. Then there's a third step where similar counterfactuals will be suppressed. So when these counterfactuals are close to each other in distance, the counterfactual with the highest affinity or nearest to fact, we will keep, and we will suppress or remove the counterfactuals near to it. And this helps us naturally enforce diversity of explanation. And that's why we are using this particular type of artificial immune system for the diversity. So we then move on to our human evaluation, where we ask people, give people a counterfactual explanation. And we then ask them to look at a task, to do a task, and we look at the results to see if the explanation is actually effective. In this task, we're using the Lending Club data set from Coghill, because lending data is the field that's been using machine learning and logistic regressions the longest, and it's the one where people are most used to seeing machine learning making decisions. We generated 3 scenarios that needed explaining. And all our participants saw the same 3 scenarios with just the explanations changing. So we started by testing our contrastive explanations with both our generation methods, which are DICE and opt-AI-net, and we tested this on Mechanical Turk. In order to keep the participants nearest our intended users, who are members of the general public, we have no restrictions on who we recruit into Mechanical Turk. So to measure performance, we're using the metrics from Hoffman et al., who suggest that we use a test of performance to measure how well people are using explanations. This performance is actually a proxy for user comprehension, but we're using this proxy measure rather than the real comprehension measure because we can apply it across all the explanations in the same way. And because it's also just a lot easier to administer because we can put it across Mechanical Turk. Whereas if we want to get users' mental models, that involves interacting with the users. And in these times, having access to actual users is very hard. So what we do in a test of performance is we give people a scenario where they've been rejected. We give them the explanation from the previous slide. And we then ask them to, then in this task, we give them the variables and the values they have, and we ask them to change those values so that they then will change the result from negative to positive. And they will be marked on if they correctly change the decision model's decision from negative to positive. We also give people a test of satisfaction, where we've just given them 6 questions about their satisfaction with the explanation and a 5-point Likert scale. This is very much the secondary test. The important one is actually, does the explanation help them change the result? So we looked at the results for counterfactual explanations, and so in our experiment, we gave people counterfactuals that were either 1 counterfactual long, so that's a contrasted explanation, we're only using the 1 counterfactual, or we give them 3 counterfactuals. We also randomly split them between seeing the explanation generated by our opt-AI-net algorithm or the existing DICE algorithm. So this is a preliminary work, so the number of participants is currently quite small on Mechanical Turk. And we have found no significant difference between using the opt-AI-net and the DICE. There is a small but not significant difference between how many counterfactuals we give them. And currently, 3 counterfactuals is slightly outperforming the 1 counterfactual, but not to a significant amount by the chi-square test. This is actually in some ways against our desiderata from earlier, because the 1 counterfactual explanations are actually more selective than the 3 counterfactual explanations. because they're shorter. So then we moved on to testing the counterfactual explanations against the feature saliency explanations. And feature saliency explanations are explanations that are of the type generated by the very popular Lyman Sharp algorithms. So they will produce a table like we have on this slide, where the explanation comes as a set of scores. So you have a feature, its value, and then the score generated by either Lyman or Sharp. And then the total, we've also calculated for them the percentage of all the weights that particular weight is. So all our feature saliency participants, they saw a table like this, and then they will also have seen either a graph or a piece of text as well. So feature saliency shouldn't actually work as well as the contrastive explanations according to our desiderata, because these are not contrastive and these are not selective. So these should produce worse results according to the theory. So each of the R feature saliency users will have seen a little bar chart of the results, or they will have seen a piece of NLG text. Both the bar chart and the text are generated using the same data, but just presented differently. And when we look at the results and we compare them to our best performing contrastive explanation, we'll see they all perform roughly the same. So this is a little disappointing for our desiderata, but it's a result. Again, we're looking at a preliminary result here. So in order to get significant results, we need 5 to 10 times more participants. We also gave our participants no explanation, where we just gave them a table of results and asked them to change, a table of values that were the inputs to the system, and we asked them to change the result. And this produced for us a rather disappointing result of it was exactly as good as any explanation we could give people. For satisfaction, all the explanations we gave them had roughly the same results, apart from the no explanation, which people really didn't like receiving, and this is not a surprise. So why is our no explanation unreasonably effective? I think this unreasonable explanation is actually giving us the mental model of the user without an explanation. So the mental state they start with unmodified by our explanations. In the instructions, we did ask people to make the smallest change possible to change the result. So when we look at the box plots of our explanations and how our model scores all their results, while it's the case that our contrastive explanation isn't any better than the other explanations, it does produce results that are much nearer the decision boundary and therefore more optimal than the other explanations do, the feature saliency explanations, and especially better than the no explanation. So what does this all mean? First of all, this really is a preliminary work where we just are trying out some explanations to see how effective they actually are. we see that our AI net algorithms are just as effective at producing change as the DICE algorithms. All our nice explanation theory that says contrastive explanations are better, this is unproven. But they're not better changing the results, but they does produce more optimal results. And that we really need to take people's existing mental models into account when we produce explanations. And thank you for your attention. And are there any questions?
So thank you very much, James. I think maybe we can ask Kyle to start off the question session.
Howdy, James. Thank you very much for a lovely talk. I promise I'm not cutting in queue. It's just the host cannot raise their hand, so I have to message the chair when I've got a question. Slightly part comment, part question. If you maybe weren't aware of the work of Judith Mastoff, she has done an interesting examination of explanation effectiveness versus explanation satisfaction, particularly examining whether explanations were effective in improving users' task performance versus whether users were satisfied to use them. And I can see your results here mirror some of the, what I guess for her were also initially confusing findings. So it might be relevant to you to go and have a look at into her work and
so
see.
Is that Mastov and Tintorev?
Mm-hmm.
Yes, it is one of the ones I'm thinking of. Yeah, I think she's got a couple that look at this phenomenon. Yeah.
Yes, of course, I do know Judith because she was here until quite recently.
Ah, fair enough. Fair enough. In which case, I apologise for jumping out there.
No, I'd actually forgotten her work because now she's in Utrecht. It's kind of out of sight, out of mind.
So, well, by all means, I think that would be very relevant for you to have a look at that, because I think she experienced similar things. I guess with the no explanation, the other point I would maybe make is, sorry, in regards to all your explanations, is that there seems to be quite a broad difference in formats. And we know from personalization research that different people respond differently to receiving their explanation in a different manner. So potentially, I would be inclined to say if you could single out a given format, either the explanations universally presented in text or universally presented as a visualization, you may find that this will increase the differences between some of these findings, because there could be outside factors at play whereby an individual prefers NLG and so absorbs more from that explanation as well.
Certainly my further work takes this into account, yes.
Yeah.
I have a major problem in that my user is also a black box, and I don't know what they want until they tell me.
Yeah.
So yes.
But no, thank you very much for the talk. That's all the questions from me.
So James, I have a question. It's regarding the evaluation. I was interested to find out, how did you use your users? Meaning, did they all see the different types of explanations apart from the no explanation, or how do you ensure that they're not influenced from the different explanation methods?
I have 3 records that I use for all participants. I was actually conducting between different explanations, it was all between types. So everybody saw a counterfactual explanation. And then there was effectively a new experiment, but using the same underlying data. And then the whole of that experiment would have just seen a feature saliency with a bar chart, and then another experiment would have seen a feature saliency with the text. And these are actually different users every time.
Okay, so you make sure that a single user doesn't see multiple explanations for the same record.
Yes.
Yeah, because that would otherwise mean the mental models are getting influenced.
No, it's fresh users every time, and everybody only sees one type of explanation.
Okay, that's interesting. I suppose one quick question before we move on. You mentioned about the OptiNet algorithm. Was there a particular reason for using that type of optimizer, and how did you check whether the counterfactuals that are generated are meaningful, because it's sort of randomly optimizing? Just any thoughts on that?
So we picked the OptAI because it comes with this inbuilt diversity where very similar explanations are removed. And in terms of, are we checking these explanations are meaningful changes? Basically, no, we're not checking that. But these counterfactuals there is some control on them, in that we pick the features that have the highest line weight, and we will just create explanations using that highest line weight feature. Only that feature can change, and then we will incrementally increase this. So then we'll add the feature with the second highest line weight, and then we'll repeat it again with the third highest line weight as well, until we've used all of the features.
So your OptAI net is using Lime as a selection method, yeah?
Yes.
Okay. That's interesting. I didn't. I guess you didn't mention that in your talk.
There was quite a lot to fit in, so
yeah,
yes.
Right. Okay. Thank you very much. So, James, I'll probably move on to the next talk now.
Okay.
So, if you can stop sharing, that would be great. So, our next talk is by Miruna Clinciu. I hope I pronounced your name correctly, and I think you're a PhD student from Heriot-Watt, yeah?
Yes, this is actually I'm from the CGT Robotics, and I'm at both universities, Heriot-Watt and Edinburgh.
All right.
Yes. So 2 seconds, I will share my presentation.
Thank you.
Yes.
Yes, I can see your screen.
Let me make it nice and tight. Okay. Okay. Good. So, hi everyone, my name is Miruna. As you heard previously, I'm a PhD student at Heriot-Watt University. And today I would like to present you our recent paper, I Don't Understand, Evaluation Methods for Natural Language Explanation. Research work undertaken by me, Arash, Eshghi, and Helen, Hastie. So through this talk, I will try to underline the necessity of finding accurate measures for the generation of natural language explanations. So do natural language generation metrics map onto evaluation of explanations? I will focus mostly on analyzing the degree to which of the automatic metrics correlates with human judgment using the X-band corpus. And additionally, I will introduce the X-band corpus, a crowdsourced corpus of natural language explanations for Bayesian networks, and I will provide a brief description of our study results and examples of good and bad explanations. But also I will say some words about the correlation between the linguistic features and human judgments. So in the end, I will spend some time talking about conclusion and future directions. So automatic evaluation of natural language explanations. As you previously heard in many talks, explanations are very important, represent a core component of human interaction. But through them, we can provide some transparency in our decision-making systems. For example, when you have robots or conversational agents, deep learning models, and so on. But the importance of evaluating the explanation has been recently emphasized by several researchers within the cognitive sciences and psychology, for example. But we should also considering the strong evaluation traditions from the field of natural language generation. So hence our question, can we adopt existing natural language generation metrics? Are they sensitive enough to capture the peculiarities, the properties of explanation of natural language explanations? For example, if you think about causality, common sense, someone already said about creativity. So it could be quite important and motivates our work to view explanations as a specific case of natural language generation and to explore mapping existing automatic human evaluation methods of natural language explanations, of natural language generations onto explanations. But also motivates our work to see if any of the linguistic features of that specific explanation can provide us some correlation between linguistic features and human evaluation. So to get a better understanding of what makes a good or a bad explanation, we created the expand corpus. What is expand corpus? It's a corpus of natural language explanations for Bayesian networks collected in a two-step process. So firstly, you have collected natural language explanations. So they are produced by human subjects. For example, you have, they receive three diagrams, three graphical representation of Bayesian networks. For example, you have in the right part, diagram 2, where you have cloudy, sprinkler, rain, wet grass. So they receive this, this simple graphical model, and they try to provide explanation with their own words. So you have natural language explanations. For each diagram, we provided them 3 diagrams. And for each diagram, we had 84 participants. So therefore, we had 84 explanations per each diagram. In total, multiplied by 3 is nearly 250 explanations. In a separate study, we tried to rate this explanation on a 7-point Likert scale in terms of informativeness and clarity. We asked the participant if how much, if they think that the natural language explanation is clear enough or provide enough information compared with the graphical representation. So in total, we have a number of 2,910 ratings. But even so, I will go further and I explain more things about the human evaluation part. But actually, why we selected Bayesian networks? We were mainly motivated by the fact that Bayesian networks are much easier to be interpreted, and they are quite frequently used for analyzing the data or approximating deep learning models. For example, in an industrial environment, they are used for detection of risks, failures in a process, and so on. So they also can use, if you provide proper explanation for Bayesian networks, they could be used also in an industrial environment, also for lay users, people that don't have any prior knowledge about explainable AI or AI. So human evaluation is considered a primary evaluation criteria for natural language generation. We selected 2 human evaluation metrics, informativeness and clarity, and we were thinking that this will be sufficient for the present research and try to clarify if the explanation will be clear enough or easily understood by users. And also, if we want to achieve clarity, then it should be easy to understand and communicate to the process of AI systems. So traditional human evaluation metrics are clearly needed for increasing transparency. So hence our focus on the human evaluation metrics from the field of natural language generation, informativeness and clarity. And for automatic natural language evaluation metrics, we use BLUES, Rouge Meteor, Bear Score, and Blur. As noted in the introduction, it remains an open question to what degree the automatic metrics from natural language generation can capture the peculiarities of natural language explanations, their properties. I speak just about informativeness and clarity, but we don't really know how to capture all the properties of natural language explanations. So in response, we ran a correlation analysis to investigate the degree to which each of the automatic metrics correlate with human judgments. Hence, here we have our results of the correlation of automatic metrics with human evaluation. As we can see, word over run metrics such as Bloom, Meteor, and Rouge presented a low correlation with human ratings. And this might be due to some certain limitations. For example, the fact that they relied on word overlap and are not invariant to paraphrases. Someone asked me previously that what for clarity we have Rouge 2 receive a very high score for diagram 2, 0.24. So this is one of the certain limitation because they rely on the word overlap, and diagram 2 was quite easily to be interpreted. A lot of participants described the notes. Therefore, you have an overlap between bigrams, and this is why it received a higher score. But every time when you have Rouge 2, you should also think about the results from Rouge 1 and try to have both results in your research or paper. You need to think about bigrams and unigrams at the same time. This is why I have also Rouge here. So, as I said previously, best score and Blauwert outperform other metrics. They produce higher correlation with human ratings than other metrics. So these are quite the recent automatic evaluation metrics. We still believe that it should be good to see these metrics try to apply this method on a bigger data set of explanation and see if they can perform the same. They have the same performance. They might capture some relevant facts of explanations, as word representation are dynamically informed by the words around them. So also in previous study in natural language generation, they can capture different dimensions. According to human evaluation scores for informativeness and clarity, we present here an example of good and bad explanations. As we can see, all metrics are reasonably good at capturing and evaluating bad examples of explanations. So everywhere we have 0, 0, 0. And indeed, we have informativeness and clarity a score of 1, which represents the bad score. But when we speak about the good example of explanation, there it's a bit tricky. We can see that just bad score and Blauwert can capture some, are more sensitive to informativeness and clarity. And also maybe they can capture very good bad examples of explanations. I believe that a larger study might be needed to show this empirically. We need to take into consideration that here we have just nearly 250 explanations. It might be good to have a bigger data set. Also, when we implemented the automatic metrics, we have some references, some gold standard. This one was extracted from the collected natural language explanation, the first stage of corpus collection. And after we selected the explanation with highest score, so informativeness and clarity a score of 7, but also was annotated by the authors of the paper. Linguistic features. I expected that, for example, if you have a very short sentence, then you don't provide too much information about that Bayesian network, that graphical representation. Therefore, you don't provide enough information, enough clarity, and it will be clearly correlated with informativeness and clarity. But things weren't as I expected. So we extracted the number of the linguistic feature. Here we have the number of nouns, the number of which determiners, number of coordinating conjunctions, and also the trace depth, and also average TF-IDF score of content words. So we try to see if we have any correlation between these linguistic features and the informativeness and clarity from 2 dimensions that I presented. We were motivated by similar study correlating features with user ratings for surface realization and from social psychology. But as I said, the results weren't so good. So, and I believe that if you have a bigger data set, then it might be better. But at the same time, we try to predict the linguistic features using a regressor, and the accuracy wasn't very good. It was 0.3 for sentence length, and still it was a very low score. So therefore, I think it should be good to find, to challenge ourselves and try to create a bigger data set of natural language explanations. So finding accurate measures is challenging, particularly for explanation. In our study, the embedding-based metrics perform better than the word overlap-based one, for example, blue, rouge, meteor. And therefore, future work will involve examining also the effectiveness of automatic metrics across a wide variety of explanation tasks and data sets. An investigation of the pragmatic and cognitive process for underlying explanation is also needed. Finding accurate automatic measure is challenging, and therefore the pragmatic and cognitive process underlying explanations such as reasoning, causality, or common sense might not be captured. So finally, the next step is to use this work to automatically generate natural language explanations for structured data, for example, Bayesian network. And through this work, we will try to contribute towards ensuring the quality of explanations to truly define good explanations. Finally, the expand corpus, and this study will inform the development of natural language generation algorithms for natural language explanations for graphical representations. So for this purpose, you can scan the QR code. And thank you very much for the interest in our paper. Please let me know if you have any questions.
Thank you very much, Miruna, for that very interesting talk.
Thank you.
So while people raise their hands, maybe I will start off by asking a question. So I guess my question, Miruna, was about the participants. So you very successfully managed to get a lot of participants. Did you use the, was it, I'm just trying to understand, was the XBAN data set already having the explanations generated, and you compared them with the explanations that the participants provided? Is that?
No. Not really. As I already said, the expand corpus was selected in a two-step process. The first time, we collected natural language explanation through a survey. We used for these social media platforms. In general, we collected nearly 84 explanations for each Bayesian network, for each graphical model. So in total, we have, for example, we have this diagram 1, or this diagram 2 with 84 explanation. We have another diagram with 84 and so on. And we didn't generate natural language explanations. We just had these explanations because at that moment, we weren't sure exactly how people will treat natural language explanation. We didn't really think about generation because we didn't know about the first step, what makes a good or a bad explanation, even for us, for humans. Yeah.
And so when you apply the NLG metrics, how do you use it in terms of, having a reference text and a candidate text? I mean, how does that part? So when you compare the text, which text do you compare?
So for example, we already provided here a reference. For each diagram, we have a reference, a gold standard. when we selected the references, we selected the natural language explanations with the higher scores in terms of informativeness and clarity. And also we annotated these natural language explanations. We didn't done too much thing about them because they were already correctly, but we wanted to verify.
All right. Okay. So basically, if I understand, the reference text was manually put together by humans.
Yes.
Yes. Okay. That I think that is what I was unsure about. Yeah. Do we have any other questions? I mean, if we don't have questions, I think we could stop now simply because we were running behind our schedule. So, Miruna, once again, thank you very much. And
Thank you so much.
I'll hand over to Kyle.
Okay, folks. Once again, we will be going into a comfort break for about 10 minutes. We'll come back at 1:15 and we will start session 2. So 10-minute comfort break, we'll come back about 1:15 and we'll be starting session 2. And in session 2, we will be looking at roles within a SICSA system and accountability. So looking forward to seeing you all back in 10 minutes.